Hello, hello. Welcome to programming class, everyone. Happy Wednesday. Hopefully everyone's having a good middle of the week. It's really cold where I am right now, so hopefully my battery is okay. But let's get started. So today we're gonna learn data types. Oh, I see a few comments in the comment section already. So welcome to everyone who's new. Looks like there are a lot of people who want to learn Python, so maybe we can dive into that some other time, maybe in another class. So far, we've been doing JavaScript for the first two classes, or the previous two classes. I don't know why I said first two. But today we're going to look at something a little bit different. We're going to look at C++ today, but really this lesson doesn't specifically have to do with any language. It kind of just is a catch-all generic data types lesson. So it'll be useful to you for mostly any other language, especially C-style ones. Maybe not for Python. Well, maybe for Python, depending on what you do in it. But if you remember from our past two lectures, when we declare a variable, we just called it variable something, right? And then that sort of indicates to the computer that we're about to give it some sort of value or some sort of data. So the computer creates space for it and waits for you to give it something, right? And then later on you can say something equals like 1 or something equals like hello, or you could give it anything in JavaScript. And you could also do this all in one line, just as a refresher to anyone who's just joining us today. Now, JavaScript is a scripting language, so you can do things like this, and it doesn't care what kind of data you can give it. It just treats everything sort of as the same thing. But most languages, what they do, at least most common languages, is you actually have to tell the computer what kind of data you're giving it. So if you ask your friend to like hold out their hand and you're going to give them a gift, they probably want some indication of like what that is, right? Like if they hold out their hands waiting for you to give them something, you're not going to suddenly pour water on their hands, hopefully. So the computer is very much like that. And today we're going to learn some of the basic data types, and they're probably some of the most common ones that you'll see around. And we'll learn how to give information to a computer. Hello, welcome. Welcome to everyone from Boston and from Indonesia. Wow, that's very far away. That's really cool that we have so many people worldwide joining these lessons. The internet is really cool. So the first thing that we're going to go over is Booleans. And I think if you've joined us in previous lessons, you've actually seen what Booleans sort of look like. Remember before we had like things that are either true or false. And that's basically what a Boolean is. It's like a little flag. It's either on or off, 1 or 0. You can think of it as any way, as long as it's like two distinct sort of states, right? International Coding Camp. Yes, that's really cool. So I guess before we do that though, the first thing I want to go over is how to just print stuff to console in C++. So I do have like this full sort of example code in the GitHub. It linked in the previous videos, so I'll actually tweet it out after too, just so it's available for you, and you can just have it as a reference or play around with it. But with C++, it's a little bit different from what we did in JavaScript. So first of all, in JavaScript, what we did before was console.log, and then we put like anything here, right, in order to like print out like words or the data that we gave the computer to store, right? And so instead of this, and you don't necessarily need to know this, you can feel free to follow along in any language that you're comfortable in, but I'm gonna go over the C++ one here. This is instead sort of how you print out things in C++. And now you're going to notice that the semicolon is very important. Remember, I told you guys that in JavaScript, it's not necessary. Like, you don't have to put it, but I encouraged you to put it because other languages make you put it. Well, now you're going to see it here. So now the semicolon is important. If I don't put this, then if I try to compile my program, if I try to run it, it's going to yell at me. And we obviously don't want the computer to yell at us. So we're going to put the semicolon. And if you take a look at this, what this does is it just prints out whatever you type in there, right? And same thing with console.log in the JavaScript lessons that we did before. You can actually put variables in here as well. So that's how we're gonna see like that the information that we're giving the computer is the same as what we intended it to be, right? And so let's start with Booleans, right? We said that it can either be true or false. So we can do like anything, like we can call it bool t equals true, and then bool f equals false. It can really be like anything you want as long as it's either true or false. And so when we print this out, if we print out t and then end line just puts it on another line, we can actually, let me just duplicate this line. We can see what the computer prints out here. So you can take a look. 1 represents true, which is this variable t, and 0 represents false, right? So now that we know that, what can we do with it? Well, remember our lesson on logic gates. Remember that we used logic gates and conditional statements. Both used Booleans. We called them variables at the time, but what we were actually using is called a Boolean. And so you can actually also use the logic gates to sort of have the computer do the calculations in its head and then store it into a Boolean, right? So if I change these to, let's say we call it is hot, right? And is hot equals true is we're telling the computer, yes, this something is hot. And then we can say maybe is sheep. We can call that true too. Let's make a bunch of these just so we can practice. And then I'm pretty much assigning them arbitrary values. So I'm making this up as I go along. You can put anything you like. You can name the variable whatever you want it. Just in your head, try to like think about what it is that you're actually telling the computer, right? So let's say is fire is false. We're going to throw a little bit of a false in there, something a little bit different. And then how can we use logic gates in order to assign another variable? Let's try is bonfire, right? Well, let's take a look. Bonfires are hot. Yeah. Let's put is hot, right? So you could already do this. This is a full statement. So is bonfire equals is hot. We'll just take this value. The computer sees, oh, is bonfire is take the value of is hot, which is true. So this is the same as saying is bonfire equals true, right? And why is this useful? Because we can use the logic gates that we learned in order to have the computer calculate whether something is true or not. So let's see, is bonfire is hot. Let's use and, right? We know our and gates. And means that both things have to be true for this entire statement to be true, right? So if we do is sheep, is hot and is sheep. So what is true and true? True and true means it's true, right? Because both of them are true. Now, if we put is hot and is fire, what does that give us? So this is true and false. And we know that both of them have to be true in order for an and statement to be true, right? So both sides of this need to be true. If you say something is true and false, then this statement actually evaluates to false, right? So the computer will think is bonfire is false. And we can actually check that. by just printing it out. Right? That gives us a 0, which is false. And so doing things like this, it makes it really easy for us to sort of know what the computer is thinking and like where it's getting the data from. We can make this a little bit more complicated by, let's add in or statements, right? So we can add maybe is sheep or is fire, right? What will this give us? Let's take a look. So is hot is true, right? It's true. We're taking this directly from what we just told the computer. And since we put brackets here, it actually means it's very much like math, right? So the computer is going to take whatever's in the brackets first. It's going to do all this first, turn it into like one temporary Boolean, and then do this statement. So it works from like the inside out that way. So actually, let's take a look at is sheep or is fire, right? Is sheep or is fire? We can just copy this over actually. Let's call it something. Bool temporary, right? So what will this give us? Is sheep is true and is fire is false. So true or false. My hands are too frozen right now. Still getting used to this body. But remember that for OR gates, what did we say? How many of these have to be true for this whole statement to be true? If I say, I am a robot or I am really tall, one of those is a lie, right? But since one of them is true, that entire statement is technically true, right? Because we're giving it an option. Warm-up protocol, maybe in my next tune-up. Need a little body upgrade. So if we say something is true or false, right, then this whole thing is true. And we can actually check that. If we print out temp, which is what this sentence is sheep or is fire, we can run it. And then you'll see, yep, that's true, which is exactly what we sort of expected from it, right? So now we know that this whole sentence, which is exactly the same as this sentence, is true, right? So if we look at this, we know that is hot is true. So this actually means true and true, right? That's what this evaluates to, true. And so what's true and true equal to? True and true equals true, right? Because both of them are true. So we can actually check this to make sure that we're not doing anything wrong here. Yeah, and that's true. 1 equals true. So cool. That's useful. And we know that all of these can sort of be used in conditions. If you need a refresher on conditions, go back to lesson 1. Or which lesson was it? It's 2 lessons back. It'll be called conditionals. It'll have a giant question mark on it. But you can go practice some of those there. But that's what the bool data type is. You can also do things like, if we want to reverse this, like bool is baba. We know that something that's baba is not bonfire. You can actually just put this exclamation mark to mean not, right? Remember, this is a not gate. And so anything you put after, it'll reverse the value of it. So if you put true after this, not true equals false, right? You can actually check that. Not true equals false. Yep, there you are. So we can also replace this with is bonfire. And so we're really just playing around with all the things that you can do with Booleans. And so Booleans are kind of simple because it's very like, it's either one or the other. It's either true or false. It can't be any other value. They're only those 2 values, right? It's only 0 or 1, true or false, on or off, right? So if we run this again, you'll see that Yep, this is the same thing because is bonfire was already true, right? And so this is a really good way for you to store things that the computer needs to remember, in like, especially in games where you have like states of like, is the game started, or like, are you alive, things like that. So hopefully that was fairly straightforward. We can actually comment all this out for now, and we'll move on to the next data type. Now the next data type we're going to learn is called an integer, right? Maybe I should write out these full things. So Boolean, integer, integer. And an integer is pretty much like math too. It's not going to be anything new. If you think about integers in math, another way to call it is to call it a whole number, right? So that's like 0, 1, 2, you know, etc. It goes all the way to infinity, you know? And it's anything that doesn't have decimal places after, or at least the decimal places after are technically 0, so they're technically there, but any whole number is called an integer, right? And so the way that we write this in most programming languages, but this one is C++, is you just call it int, right? We can do int a equals maybe 1, and then we can keep going sort of like this. Int c equals, we can call it like 5. You know, it's very much the same as like in math when you assign variables. Like you can say like int x equals like 100 or something, you know? So all of these are basically numbers that you're giving the computer, and you're calling them these names. So the next time that you tell a computer, hey, I want a, or use a to do this, like they know what a means, right? And so ways that we can use this are very similar to real life approaches. So what can you use numbers for? What can you do to numbers? Well, something easy that the computer can do is it can add numbers, right? So you can do 1 plus 1, maybe, right? And then let's print that. What's 1 plus 1? Hopefully everyone knows this. But if you need a refresher, the computer's got you. It's a 2. And we don't have to type the numbers directly, right? We can use variables to assign values to other variables, right? We can make variables out of variables that already exist, right? It's like building blocks. So we can use these building blocks to make a new integer. Or you can just change the value of an old one. So I'm going to keep using add. And let's try doing like a plus b or something, right? And if we look back, like the computer looks at a and says, oh, hey, I know what that means. A means 1 and b means 2. So the computer is going to add this together, right? Which gives us 3. Yay. So that's exactly what we wanted from it. Now, other things that we can do, obviously, if we can add, then we can subtract, right? And so you can do like 1 minus 1, and then we can just take a look at like what that does. We're doing this like kind of slowly, so hopefully it's at a good pace for everyone. So yeah, 0. We're just checking all of our assumptions right now to make sure that I'm not lying to you guys, you know? Good evening, Dylan. Welcome to Data Types. All right, so, and same thing with addition. We can do like b minus a or something, right? And the computer looks, oh, that means 2 minus 1, right? Which gives us 1. And that's exactly what we expected from it. Cool. So now that we have subtraction, obviously there's also like multiplication, right? So these will all be a little bit straightforward. We're starting off like really slow with the sort of easier data types to understand. And then we're going to move our way to more complex ones. They're not going to be like too complex, but they're going to be a little bit past like addition, subtraction, you know, those types of things. So I'm sure everyone has already learned their addition and subtraction from Miss B's class. But multiplication, we're on multiplication. Let's see, what's 1 times 1? This should be pretty easy, right? Obviously 1 times 1, anything times 1 is 1. And you know, this is kind of useful. This is kind of like a calculator. Obviously the computer can do things that are a little more complicated than this, and it does things a lot faster than we can. So if we like do really big numbers, we can do that. So that's 9,999 times 9,999. And it does that like in a fraction of a second, basically. It does it super fast. We can also do the same with variables. So we can do like a times b, which is what we've been using since the computer already knows what a and b are. A nice thing about that is like if we do want to like change any of these values of add, subtract, or multiply, we just need to change it in one place, right? If we want a to be like 100 from now on, we don't have to go into each of these and change like 100, you know? Since the computer knows that a is linked to this number, whatever number you give it, it'll replace it in these equations, which is super useful, right? Yes, we'll get to strings soon. It's a little bit of a spoiler over there. We'll get there. We'll work our way up. But so, now that we know this, let's change a back to 1 for now. Division is where things get a little bit different from what we know in math, right? So for division, like we can start with something simple like 1 divided by 1, and that's obviously just 1, right? Yep. Oh, that's 2 for some. Oh, it's because we're printing out multiply. We need to update that a little bit. So 1 divided by 1 is 1, right? And so what about, here, instead of doing this, what about 1 divided by 2? Does anyone know what 1 divided by 2 is? Here? What will the computer print out for us if we ask it to give us back this value, 1 divided by 2? So if you said half or 0.5, you would actually be wrong. It gives us back a 0. Why is that? Why is it? Why is 1 divided by 2 0? It's obviously more than 0, right? But remember that we're using integers to store this in. The computer is storing 1 divided by 2 as an integer, which is a whole number, right? So it gets rid of all the decimal places. It doesn't know what to do with them because it doesn't have space for it, since we told it that, hey, we're going to give you an integer, right? Yeah, exactly. You can't have decimals. And so normally what we would do in like math class, for example, is like as students, we would maybe round it, right, to the nearest 0.5 or to the nearest whole number, I mean, depending on like how high or low it is compared to 0.5, right? You'll remember like rounding rules. So maybe that's the problem. What if I do 1 divided by 4, just a quarter? What would that give us? Actually, maybe let's do 3 divided by 4, so it's closer to 1, right? What is 3 divided by 4? Still 0. How come? Well, that's because the computer doesn't round this. The computer takes this very literally because we haven't told it to round anything. We just told it, store this information into an integer, right? And the way that it stores this number into an integer is it takes whatever number is in front, the whole number part of this, right? So this would be like 0.75 normally in human terms, you know? If we were using decimal places, it would equal that, right? But since it's an integer, the computer says, oh, well, we want it to store this part, just the 0. And so it takes everything after it and just gets rid of it. It doesn't need to store it because it doesn't want to waste memory. It doesn't want to waste like any space storing things that we probably won't need because we've told it that we don't need it, right? By declaring this as an integer, by saying, we're going to give you an integer, the computer knows, or at least it thinks it knows, that we know what we're doing. And it does exactly what we tell it to do. Some languages do automatically round. A lot of them don't. The behavior here for a lot of data types really depends on what language you're using, but I'm going to teach it to you in like the most generic way possible, where it's applicable to like a lot of the more common languages. And so integers in that sense, most of them will just get rid of all the decimal places. What would happen? Oh, here's a question. What would happen if we did 4 divided by 3? Let's work it out before we ask Mr. Computer here, right? What is 4 divided by 3 normally? That's like 1.333333333 repeated, right? And we can keep going for however long we want, right? ... to whatever decimal place you want. So we know the value of that. So we know that the computer doesn't round this. It just takes this number, right? So the computer sees 1, and then it doesn't go on anymore. It knows, okay, I just need 1. So in that sense, it's a little bit like the computer does like long division. You know, if you've ever done the thing where you put like a 4 on the inside, and then you put a 3 on the outside, and then you just put a 1 on the top. That's the value of it. And then we pretty much just get rid of the remainder. We throw that away because we don't want it. And we can actually check our math here. Yep, that's a 1, right? And that's kind of what we expected out of that. So same thing here. We can also divide using like our variables here. We can pick anything we want. Like we can do like d divided by c. That'll give us 10 divided by 5, which is actually an integer, right? Because it's a whole value. It should give us 2. Yep, there it is. It doesn't return an error. So that's the nice part. Like the computer assumes that we have the best intentions, right? And it would kind of be annoying if every time you gave it some sort of data, it like nitpicked at you and said, hey, that's not okay. And sometimes the computer does do that. But in a common case like this, there are actually real world applications where you might only want the first number. You might only want the integer value of it. And sometimes that's okay. So for the most part, the computer will sort of give you the benefit of the doubt here and say, okay, well, that's what you want to do. It doesn't question you. It just does it, right? But no, it doesn't give you an error. For the most part, in terms of data types, and obviously I'm generalizing a lot to like across all programming languages, even though like some programming languages handle things differently. There are always like exceptions. But most programming languages, when you declare a certain data type and you give them something that's not that data type, the computer will just assume that what you gave it is correct. So for example, like if you tell the computer you're going to give it a fruit and you give him like a sheep instead, right? The computer's going to treat it exactly like a fruit. Like it's going to try to convert it to the nearest fruit that looks sort of similar to a sheep. It's going to try to maybe like eat the fruit. It's going to try to make juice out of the fruit. And what you gave it is really a sheep. So the computer assumes that you don't lie to it. And it does the best that it possibly can based on what you give it and what you tell it you're giving it. Exactly. It's okay to be wrong, human. The computer is nice. He will try to do whatever he can for us, and try to yell at us as little as possible. Although he can give us warnings, you know. If we give it the wrong information, it'll raise some alarm bells. And most languages will tell you, maybe this isn't what you meant to do, but it's going to try its best to accomplish it anyway. Right? And so, yeah, we saw d divided by c, 10 divided by 5 is just 2. And we can honestly do the same thing the other way around. C divided by d, which is 5 divided by 10, which is just 1 divided by 2 if you simplify it, right? So that's going to give us 0, right? Hopefully that was all straightforward so far. Booleans and integers. Let's take that out now and move on to something called doubles. And doubles are exactly what we need when we try to divide something. It actually has decimal values. Now, there are a lot of similar data types to doubles. There's something called a float, which is just like a double with less space. So it can have slightly fewer decimal places. There's something called a short, something called a long. There are a variety of data types that have decimals. Doubles are very common, so we're just gonna use doubles. Most of those data types are treated pretty much the same way as doubles, right? So the way we use doubles here, you can think of it as sort of interchangeable between any of those data types that I just showed you, like short, long, float. Doubles are just kind of common. Doubles and floats, I guess, are the most common. Well, I don't want to say they're the most common. It really depends on what you're doing, but for our purposes, just use a double. Yes, do not make computer science memory leak. Be nice to your computers, ladies and gentlemen, and other folks who are in the audience. Okay, so with doubles, we can pretty much do the same thing using doubles as we did with integers, except now we can have decimal places, right? So, okay, we can use like A again. Let's use the same values that we did actually. So A, B, C, and D. We did like 2, 5, 10. We'll just like copy this all over, right? So these are the exact same values, but now instead of telling the computer that we're going to give it an integer, we're telling the computer, hey, store these in a double instead, right? We're giving you a decimal number. And so now that we have that, what if we put this answer into a double as well? Like we can put 1 plus 1 here, right? Add, and we're just like printing it out here. So 1 plus 1, like even if the computer interprets these as integers, it'll store the value into a double. And so what I mean by that, we can sort of go over that a little bit later. But for example, we can do like 1.2 plus like 3 or something, right? It can be anything we want. This is basically us just playing with a computer. It's like playing with a calculator right now. She gives us 4.2, right? A double will look very much like an integer if you don't put any decimal places. Like it doesn't have to have decimal places. It just gives you the ability to put decimal places, right? To use them. And so we can do like pretty much exactly the same things that we were doing before. Except now, let's skip all of those because we've already done those with integers. It's really redundant to do them with doubles because they're just numbers with decimals, right? Whether or not you use decimals is just up to you. So with division, let's actually try division here. So now we can try 1 divided by 2, which is what we were trying before, right? 1 divided by 2. Now what will this give us? If we run this, we called it add, but we got rid of add. So the names are important. It gives us 0. And the reason for that is because the computer is treating these two as integers. So it's actually seeing that, oh, 1 doesn't have a decimal place here, and 2 doesn't have a decimal place here. So it's just an integer divided by an integer again. And how we fix that is we turn one of them into a double, right? And we can just put like 0.0 into one of them. We can turn like either of them into a double like this, or you can just turn 1. As long as one of them is a double, it'll give us a double as the answer. And so if we do this, yes, now it gives us 0.5, which is more of what we expected, right? And let's sort of break it down into, I guess, the different combinations of doubles and integers, right? And so if we do like a double divided by an integer, right? Which is like this. 1 divided by 2, right? That'll give us a double still, right? Because remember before we did like 1 divided by 2.0, which is an integer divided by a double. A double is just whenever we have decimal places. Another way that we can do this is 1, the computer will read as an integer, right? Like we said. If we take b, the computer already knows that b is a double, even though we didn't explicitly write 0.0, right? We didn't tell it that it has decimal places, but it knows that b is stored as a double because we told it b is a double. So what would happen if we did 1 divided by 2 where b equals 2? Let's take a look. This will give us 0.5, right? Because at least one of these two is a double. And we can sort of do the same thing with 2 doubles. It doesn't matter, as long as one of them, at least one of them is a double, right? Hopefully that was simple enough to sort of understand. So that's doubles. What else can we sort of do with doubles, right? We can do a lot of things with them. Remember when I said doubles or integers, computers don't generally round integers automatically. You have to like tell them to do that. So what if we had let's say 1 divided by 3, for example, right? And we make one of them a double. How many decimal places will this give us? Well, this defaults to 6 decimal places. But what if we have a specific number of decimal places that we want, right? Obviously, we want to be able to like tell the computer how many decimal places that we want from it. And so an easy way to do this is to use a function called round. So this is going to look a little bit confusing, but basically we tell it to round using this function. It's like a tool that already exists within this language. And so we're telling the computer, use this tool on div. And the way that we specify the number of decimal places is we multiply it by 100 for 2 decimal places, or however many zeros that you want behind the point. And then you divide it by 100 again, right? And so what this gives you, whoops, hang on. Round cannot be used as a function. It's because I named this the same as round. So since round is a word that's it's sort of already assigned to the tool, we can't call our variable the same thing as it. It's the same thing as like you can't call a double because this double is already a keyword. So that's why there was the error. But if we make run this now, we didn't print out the right thing. If we make run this now, it shows us 2 decimal places, right? And we could like keep going. If we add another 0, it'll show us 3 decimal places. This is sort of just the format that this round tool takes from us, right? And if we did like 10, it takes like the number of zeros is the number of decimal places, if you want to think about it that way. And so that'll give us 1 decimal place, right? Everyone with us so far? Now there are a few other functions that we can do on doubles. There's also something called a floor function. I'm going to make sure I don't call it floor again. But a floor is basically, if you think about it, it's what integers do when there's a double. Like for example, let's take 1 divided by 3. What floor does is it basically always rounds down to the nearest, or not the nearest, but the lower whole number. And so 1 divided by 3, remember this gives us 0.333333, right? 0.33333 forever, basically. And so if we floor it, what will happen is we'll just get a 0. Oops, I didn't run it, right? Because the nearest or the lower whole number that's closest to 0.3333 is just a 0. There's also something called a ceiling function. And what ceilings do, I can't call this ceiling. I'll call it ceiling. Floored and sealed. Hands are too cold. Floored and seal. Seal works kind of the same way, but in the opposite direction. So it always rounds up to the higher bound of the whole number. So 0.3333, if you think about it, it's already past 0, so the next closest thing is just a 1. And so we'll see that if we print out sealed, that'll actually give us a 1, right? 1 divided by 3, all sealed is a 1. So hopefully that made sense to everyone. What else can we do? We can also square root things. Basically all of these are just like different math functions that you can do. And all of them are pretty useful on doubles and in just programming in general and in math. You'll see these used a lot. Squared. We'll call it squared because this is just square root, right? So if you square root something, we can maybe do like 100. What's 100 square rooted? 100 square rooted, whoops, like run, is just 10, right? And so these are all sort of tools that the programming language has to work on numbers. And honestly, like, I could have made this an integer. I could have made any of these integers because none of them give something that actually needs to use decimal places, right? So we can print out 10, and an integer means that the computer has to dedicate less space to it. So every time we specify a double, a computer makes way more space because it's expecting us to have decimal places, right? And that means that the number that it's storing is most likely bigger than an integer, right? Like if you take a big integer, maybe like 1,000 or like 10,000, if you think about something with like a lot of decimal places, like maybe like 1 divided by like 17 or some prime number like that, right? Like it can get pretty big, especially like even this like 1 divided by 3, oops, 17.0. Remember, we need to make one of them a double, right? It can get really long. And especially something that was like repeated forever, like 0.33333, it's gonna store like as much of that as it can before it like throws the rest away, right? And so if we tell it that we want a double, that means that the computer saves more space for us, right? It'll maybe hold out like both of its hand instead of like one hand because we're telling it, hey, the thing that we're giving you might be kind of big. And that's why, like, if you can use an integer, then use it because it's a little bit more efficient for the computer to handle. But obviously, if you know that you're going to need decimals and you don't want to deal with like conversions or anything, then doubles are the way to go. Or like any of the alternatives that I listed, which are like floats, shorts, long, depending on like how long you think your decimal places are going to be and how much of that you want to keep, right? So the computer is nice to us and we have to be nice back to it, you know? Kind of works both ways. It's a two-way street that way. Cool. So that's doubles, right? That's doubles. Now let's move on to something that's not so mathy. Maybe a little bit mathy, but not too mathy. Something that humans kind of understand a little bit more. And that's characters, right? Characters. What is it referring to when we say characters? Like, is it like Mickey Mouse. Hopefully saying that doesn't get my channel striked. Is it, if something is like a character count, what does that mean? That means like letters, right? Like in the alphabet. And so like if you say like a character A equals like the letter A, like you can do that. Or like you can call it anything you like. You can call it CH or like Bob. Whatever you want to refer to this value as. That's what the computer will reference. That's what you'll call it when you're telling the computer what you want to access, right? Yeah, you can call this bonfire if you want to. You can call it anything. And if I just print that out, bonfire, it'll just repeat back the letter that I gave the computer, right? And so why is this really useful? Why do we only want like something that only stores like one letter and not like multiple letters, right? And so the nice thing is that similar to like integers and doubles, if you know that you only need one letter instead of like a full sentence, then obviously it's a lot faster and cheaper for the computer to store this. It's not very demanding. It's like very fast. It knows exactly how much data to store, right? And so some fun things with this is you can actually put like emojis in here too if you really wanted to. Or you can basically, you could treat characters as like some sort of like number too, which is like how the computer can sort of represent it, right? So let's just make a bunch of characters just for fun, and then we'll see what we can do with them, right? And so if this isn't your first lesson, then you might be seeing where I'm going with this, right? And now, wait a second. For the I actually want this to be a single quotation character, but that's how we specify a character, is we cover something in quotations, right? Like we had character letter equals A. That's how we tell the computer that this is a character. So how do we write this? Well, what we can do is we can escape it. And this backslash is telling the computer, hey, don't take this as like part of the code. Take this as exactly this character, right? And so if we print out I, it'll actually just print out one single quote, which is what we wanted, right? And so we can do more things that are like a single character. We'll put like a mouth. What do you guys want to use as the mouth? We'll use like a little pout maybe. That'll be fun. And so you can use characters, you can string them together into sort of anything you want. Like if you want to do like, you can print, let's do the left first, and then we'll do an eye, and then we'll do a mouth, and then another eye, and then the right side ear, right? What will this print us? So you can sort of act like the computer right now and take a look at what's left. So it'll be like this, and then we'll take an eye, which is the single quote. We'll take a mouth, we'll take another eye, and then the right ear. So what will this give us? It makes a little me, right? So those are sort of like fun things you can do with characters. And characters sort of like leads us into strings. Like obviously when we're printing this out, if we want to store it in something else, like we can't store it into another character, right? Like you can't sort of store two characters in one, right? You can't do like A and B at the same time because this is more than one character. It goes past like what space that the character or that the computer made for it. So you can't do something like this, and you can't like type full sentences, right? And you can't type full words. So characters are a little bit limited in that way. What you can do actually though is add characters. And the reason you can do that is because the character has the computer has an internal value assigned to all different sorts of letters and characters. And that's something known as ASCII, if you've ever heard of it. And so, you can actually see if I add A and B together as characters, whoops, I didn't print it out, sorry. If we see out here, what'll this give us? This will give us some other ASCII character, right? If we do A plus 1, what's one character after A, do you think? What do you think the computer will think that is? A B, right? Because A, the letter A plus 1, one character past it is B. And you can do the same thing plus 20 to get other letters of the alphabet, which is kind of fun, right? You can do math on letters, which is kind of weird. Also, interestingly enough, right, lowercase letters are, their codes are a little bit different than uppercase letters. So if we did a capital A plus 1, what do you think that'll give us? I'll give us a capital B, right? So it's fun that way, in that you can sort of manipulate characters that way. And we're gonna learn about that a little bit more once we learn how to convert characters to their values, right? If you actually want to see what number the computer has assigned to each of these different characters, you can actually go online and search for an ASCII table. I'll type it out for you. An ASCII table, right? And you can actually see a chart of what letter or what character any number is assigned to for the computer. And so Unicode characters sort of work in a similar way, but they go a lot higher and there are a lot more of them. But ASCII is pretty much all the alphanumeric numbers and letters, right? You could even put a number into a character, and it'll take that as the character itself, right? So that'll give us a 1, but this time the computer doesn't interpret it as an integer. It's interpreting it as a character, which is really exciting because you could technically do addition on this too, and it'll work because the next number over from 1 is 2. Now, obviously you can't do multiplication or division on this, right? That doesn't work because, okay, well, I guess you could, but it's not going to work the same way as how math normally works. Because, for example, 1, if we go to the ASCII table, let's go take a look at it. I guess 1 is stored as 1, but if you do A divided by 2, for example, the value for A, if you search it up, you'll see is 67, right? So you could actually divide it by 2, and that'll give you a different character, right? But it'll be something that's different than what you sort of expected. So you can do math on letters. That's what I want you to take away from this. And so now that we know characters, how do we use characters to form words? How do we use more than one character? How do we make a sentence out of it, right? And so that brings us to something called strings, right? Strings use double quotation marks instead of the single quotation marks. And so with a string, you can actually type AB or a sentence. Whoops. I forgot to name the string. Let's call it S. Right? So, and we need to print it out so you can actually see what I'm doing and what the computer is doing. Okay, so now that you see that, AB, right? That's what you're putting in here. And so for example, you can put string name, and then I can write my name is Aki, right? So I'll fill that in. Professor B isn't gonna like it when you add x plus y. Maybe she'll like it. I don't know. Don't tell her I taught you that. Just tell her it was someone else. Some other android. This is not the droid you're looking for. Okay, so that'll print out ASCII, right? And obviously, like, I can make like a greeting. If I type like a full sentence, you can go like, hello, my name is ASCII, right? You can do something like that. And then if you like, whoops, greeting. If you print that out, it's going to tell you, hello, my name is ASCII. Now, how can you use strings together? Like, remember how we were using variables within other variables to create new variables? So we're using variables that we already have, so we don't have to type it again, right? And what if we wanted to change our name, right? So what if we use the name variable with the greeting, right? That would be pretty nice. So we can actually make a new string here. We can call it anything we like. I'm going to call it S for now. Obviously, normally you would want to use like something that makes sense, but we're going to be a little bit lazy here. You can actually add strings together. And what adding strings does is it'll just put one string at the end of another, depending on like which direction you did them in. So you could do like greeting plus name here, right? And so if you print out S, what will that give us? Hello, my name is ASCII, right? And now this way, if we only want to change the name, ASCII, right? We can put, hello, my name is Bonfire. We don't have to change like every instance of it in this sentence. Like imagine if we put, hello, my name is ASCII, and ASCII is tall, and ASCII, right? Imagine if we did that. That would be awful to just like go in and replace. We'd have to like do all this, right? But instead of that, what we can just do is like use one of them as the variable. And then what you can do is you can say, hello, my name is, put another string here, plus name, plus, and like obviously this is a little bit more setup at the beginning, but afterwards you're gonna thank yourself because this is actually a lot easier, right? Plus name, plus space, plus name. It does get a little bit sort of annoying to set up, but once you have this, like let's print out greeting here, make run, and we say, hello, my name is Bonfire, and Bonfire is tall, and Bonfire, right? So that's kind of our sentence. We can change this whenever we want. My name is Bob, and it does it really fast, right? And obviously in like a setting where you're actually trying to use this code and make this sentence, like you obviously want to be able to replace it as fast as possible instead of like looking through all of your code. Like imagine if this wasn't one line and if this was like a full program with like multiple files, right? And then you sort of like have to Control F and like look through every instance of like ASCII or like Bonfire or like Bob, and then you have to replace it that way. That would be a mess, right? And like imagine if you were trying to replace something called Bob, and then there's like another variable called like Bobble, right? And you have to account for like all those things. So it's a lot easier if you just use a variable instead of like putting the exact thing into your code, right? Because if you can do it manually, then you don't need a program, right? There's no reason that you would want to use like a program to like do it. Like why does the computer need to do it if you can just do it, right? Obviously because the computer does it faster, and because that way you can use it with like all different types of data. Can characters be added to strings? Yes, they can, which is actually really neat. So if we say name is like Bon, right? You can add an F to it, right? That's a character. Make run. Make sure we're printing out the right thing. And that gives us bonf, right? Which is really cool. And then you can actually do like strings plus strings, right? Or sorry, characters plus characters. A character plus a character is a string. Whoops. Oh, it's because it's trying to read this as an integer instead. But what you can actually do is like append. So if you say like string s equals like a. So this is what I mean. Like some languages have a lot of quirks like this. But you can actually like append like f here. It's like a different way to get it to do what you want it to do, right? Oh, it doesn't like that. I remember. Okay. So append in C++ is actually a little bit different because it actually returns a string. I forget what the actual function for it is, but you can search that pretty easily. Yes, strings are stored as a bunch of characters. You can actually technically add integers to strings in most languages. I'm pretty sure you can't in C++. Because C++ uses something called string streams, and that's just like sort of a quirk it has about it. In other languages, for example, like if you're using like Java, or I think even Python actually, if you did something like this, if you did something like this, then it would actually turn one, since you're adding it to an empty string, it would turn one into like a string that says one, you know? But this obviously doesn't work in C++ because it has like a different way that it's trying to interpret it. And so there are like little language quirks like that. And those are like the parts that you learn as like you're doing the language. Or if you switch between languages a lot, then it's usually just a quick search away. And it's really not a big deal. Like we're really just learning things that are applicable across like more languages. So the way that C++ handles strings is a little bit different. But in other languages, you could do that, for example. So what else can we do? We can add formatting to our strings, right? String quote. Remember how we said if we wanted to add like a single quote to a character, we use the backslash in order to escape the character so it knows that it's not part of the code. Well, you can do the same thing with the double quotes for strings. Hello, right? So we can put the quote here. And that'll give us 2 double quotes. Because if we didn't put that, then the computer actually thinks, oh, this is a string and this is a string. And then I don't know what the fuck you're doing here, but okay. So that's going to give us error, right? Yeah, there's an error. Cool. So that's one way to add double quotations. What about things like tabs? How do you add a tab to this, right? And one of the ways is like, can you add like a tab like with your keyboard? And sort of sometimes you can do this, but it's not completely consistent. I can put an A here just so we can see like the spacing, and it does sort of work. This is a tab character and it'll work for most purposes, but imagine looking at code, like especially here, like it's really hard to tell like if these are spaces or tabs unless you highlight it, right? And so we want to sort of get out of having to deal with that, right? And so a way to actually write out the tab explicitly is to use an escape character, which is backshift and then T, right? Backslash T actually will give you a tab. And here, it might be easier for you to see if we put it in here. So we'll make a new string called tab. And in the same sort of concept, we can do like a new line that way too. And the command for that is just backslash n. And so when the computer sees backslash T within a string, within these double quotes, it says, oh, this is a tab. It can recognize it. And if it sees backslash n, it knows, oh, this is a new line that I should do. I should write everything after this on a new line. So for example, if I put \n here, right, you would see hello in quotes on one line and then a on the next line, right? Kind of like that. Hello and then a. So we just kind of like took it out by assigning them to strings called tab and new line. But this way, like, you can sort of see what we're doing here. If I put like plus tab here, make sure that all the quotation marks are right. Whoops, tab was not declared in this scope. Oh, I accidentally copy and pasted this out, or cut it out. So if we do that again, you'll see here's a tab, right? And then if we change this to new line, it's a hello in quotes plus a new line. And then on the next line, we write a. New line. Oh, I see what I did. I accidentally dragged tab over like this, and I didn't even notice. But yes, now that we have everything fixed out, that's sort of what we expected, right? So cool. That's like a bunch of stuff you can do with strings. There are actually more things we can do. Why not? Let's make bonfire here, right? We can actually make emojis here, right? If we do like bonfire is like a sheep, and then we can do like maybe string fire equals this. You can do a lot of fun things with strings. You can put a lot of characters in here that don't make any sense. Like if you've ever seen like the nightmare text, like Zalgo or anything, you can put all of those here because they're at their core just characters strung together, right? And so like if I print this like bonfire, right, you can actually see there's like a little sheep there. What else can we do with this? We can, yeah, that's about it. There's like different things that you can sort of like add, but at its core, like these are just like things that you can put text in. And text is at its most primitive sort of form, just characters. So in most languages, not all of them, in most languages, strings are basically just a long list of characters. And that's kind of how they're treated, which is why like in most languages you can add strings to characters add characters to strings and add strings to each other and do all sorts of like wacky things like that. Like, for example, we'll learn this in the next class, but if you were to like treat it as an array, usually what you can do is like you can even take out each of the characters by referencing which number it is within like this order, right? Like it's taking from hello, my name is, right? We took the first letter out of that and it's H, right? We can take like the maybe like 10th letter of that. And since it starts at 0, 10 is 9, right? Which is a little bit confusing, but yeah. Let's see, we can count 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, right? It's an N. Because it's counting spaces are a character too, right? Anything that fits on like one space within your text editor here, because you'll notice that like all of the letters here are like exactly the same size, right? This is what we call like a monospace font. Like anything that fits in like one space is usually a character, right? You don't have to worry about arrays yet. We'll go over that in the next class. We're just going over like the data types today. So let's get rid of all of these now, right? What's the next thing we can do? Now that we have these 4 data types, right? These are like the most common ones and the most important ones. So just make sure you remember them. You're probably going to be using like doubles and ints, or 5, I guess, because we have Booleans, but Booleans, integers, doubles, characters, strings, those are like pretty much usually all of the data types you need. They're like pretty applicable to most purposes, and they're usually like all you need. There are a lot of other data types, but these are like the basic data types that everyone should know. And like once you know this, you know a lot of programming already for like general purpose programming, right? And so let's have some fun with like changing these types from one to another, right? Like the first thing that we can try is like integers to doubles, right? And obviously like we've already done a little bit of this in trying to like divide things earlier. And so what we can do is, for example, if you have like an integer, right? And then you want to, let's call it like I, integer I, and you give it like a double, right? Now, obviously, see out. Obviously, an integer isn't enough to store this because remember, it doesn't make any space for decimal places. So what will this actually give us? It'll give us a 1, right? Because what the computer is doing is it's actually looking at this. Remember how I said, like, if you give a computer something and you tell it what type of thing you're going to give it, the computer is going to take you at face value. It's going to believe you. So we're telling the computer we're going to give you an integer. And we give it something that kind of looks like an integer, but it's not really an integer. But a computer knows how to turn this into an integer. It just takes this off and stores it as 1, right? And that's kind of similar to what we saw before when we were like dividing integers by each other. It just ignores everything else because it's not important to it, right? And so an explicit way to do this is actually just to do this, is to put in parentheses like what type we actually want to convert it to. And so in the computer, this is actually what's happening, but the computer is like assuming that we want to do this, right? Now, if we type it like this, then the computer knows for sure that that's what we want from it. And sometimes this will save us because the computer doesn't always make the right assumption. It does its very best, and it is usually pretty good at guessing what you're trying to do, but sometimes it can come up with unexpected things, right? Don't lie to the computer. Exactly. Don't lie to computer. So we can do something very similar with doubles, right? Double D. Oh, I don't know if I named that the best, but just ignore that. Just don't say that full sentence. But this double, what if we put a 1 in it, right? And we said that when we type a 1, a computer automatically thinks, oh, this is an integer, right? Because a computer doesn't make space for extra things that it doesn't think it'll need. If it sees a 1, it says, oh yeah, there are no decimal places. It's an integer, right? So, oh, we didn't print that out. Sorry. So if we print that out, and actually what we should do is we should print out what type it is too. So let's put a space here. And then I'm going to use a function. You don't have to remember this, but this is basically how we're going to make the computer tell us what it's storing D as, right? So, for example, okay, instead of doing that, let's try 1, right? Let's put 1 for now and see what type the computer is storing it as. Because we haven't told the computer, right? This is one of those times when the computer is just going to assume something because it sees a 1 and it doesn't know what that is. Or, I mean, it knows what that is, you know? So if we do this, 1 is type integer, right? So that's what we expected out of it. Unless there are viruses, yes. But for the most part, with a virus, a computer is still doing what it thinks you want it to do. It's what the virus is telling it to do instead. So it's a little bit conflicting there, but the computer is not at fault in that case. And so let's take a look at D. What do you think D will be here? We've told it put this integer into a double. So surely it gives us back a double, right? And yeah, 1, which is D, is type double. D for double. So that's exactly what we wanted from it. We can do the same thing with I just to check, right? Remember I was 1.25, right? And then 1 is what it casted into because it's getting rid of 0.25 is the type integer. And we can actually do the same thing here so you can see like what's happening. 1.25, right? Let's do 1.25 here. 1.25, this is going to show us that 1.25 is double, right? 1.25 is a double. Now what happens if we put an integer cast in front of it? This is an integer cast. When you put like a data type in parentheses in front of whatever value that you're feeding the computer, right? It doesn't matter if there's a space or not. The computer doesn't care. It's mostly for our readability. So if we do this, then it sees 1.25 is type integer now because we added, we turned it into an integer using this integer cast, right? Hopefully it made sense to everyone. Another thing that we can sort of do is we can convert characters to integers and vice versa too. And honestly, like with all of the variable types that we learned today, like you can cast between any of them in ways that make sense, right? Like you can obviously cast an integer to a string. Just in C++, it's a little bit different. So things that are like strings are normally a little bit different depending on what language you're using. But for the most part, integers and doubles and number type of things are very similar. For example, you could also use a Boolean here, right? We'll call it bool T for true, or maybe bool B for bool. All right, and then we can print it out. B is type B. Let's see, what will this give us? It's a bool, right? B for bool. And so what happens though if we cast this to an integer, right? Remember, we can cast something by just telling the computer what type this new thing is. But let's put B inside of I. What do you think that'll give us? So we're saying take this bool B and stuff it inside of an integer. And we've already called the integer something. This will just overwrite the value. So it's erasing this. The computer erases that because it says, oh, you want I to mean something different now. We don't need the old information, right? So it's like this line didn't exist. So if we put that, whoops, make run, then you'll see it actually prints out a 1 because 1 equals true, remember? So 1 is the type integer now, which is, yeah, exactly what we want. If we made B false, what would happen? Remember, if 1 equals true, what equals false? 0. Yay. And now we get an integer back instead of a Boolean, right? So cool. Hopefully that makes sense. Let's try characters to integers. Now this is where it gets a little interesting because these values are really like in the table that I told you about, the ASCII table. So that's what the computer is just arbitrarily assigning something. And the way it does that is sort of whoever makes the language, there's like a whole history behind it, but the table exists somewhere in the computer's memory already. And it's pulling from that to tell you which character to display and which character is in its store, right? So if we did like character C, right, equals like A, what is that if we stuff it into an integer, right? Equals C, right? Let's print that out. What is that? 97. So now you know that a lowercase a equals 97 to the computer. And if you search up an ASCII table online, you'll actually see that, yeah, that lines up with exactly what value the computer stores for A. The fun part is doing a capital A is actually like a completely different number. That's actually 65, right? If you search up a table, look at it, you'll see what I mean. It's a lot easier once you have the visual there and you can see yourself, like what number corresponds to what letter, right? You can do the same thing with like a 1. And a 1 in integer is actually just 49. So that's always fun. But once you take a look at that, it makes a lot more sense. Okay, so now that we know that, can we do it the other way around? Yes, capital A is less than A. And the reason for that is because, so the chart goes something like this for the table. So 0 to like something like, what was 1? 1 was 49. So like 0 would be 48, right? Anything before that is like a bunch of different characters. Like I think it's like the null character and then like tab and like new lines and spaces and exclamation points, punctuation marks. Those are like 0 to 47 or something. Once you reach 48, it's like 0 to like, it's like all the digits, right? 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. And then I think there's like a bit more punctuation in the middle before like the capital letters, right? The capital letters, remember, it starts at A, which is 65. And then there are like 26 letters in the alphabet. And it goes up to like, I think 90 for capital Z, right? We can actually just check this. Why am I just guessing right now, right? So 90 is Z. And then I think after this, it starts doing like some crazy characters. But the way that we can check that actually is if we do the opposite way instead, if we do like I equals, let's do 91. Let's check what value or what character this value of 91 corresponds to. And we can actually say it's I, right? Oh, whoops, we need to print out the right thing. Make front. Oh, it's actually a square bracket. Okay, and we can actually keep doing this and just take a look at like what values they actually are. The next one is like a backslash. And then I think all the way up to like, what was it? Like 97. If we go to 97, it should be a lowercase a, right? There we go. Yeah, that's how it works. It just keeps going. We can actually like check any number here, but what we're doing is just implicitly converting this number, this integer, to a character, because we're telling the computer that, hey, we're gonna give you a character, and then we give it a number, right? Well, the computer knows that this isn't a character, but a computer has a way to convert this number to a character, which is what it thinks you want. And so it just does that behind the scenes because it assumes that you know what you're doing. It trusts you. It's your friend, you know. And so that's what it does. You could do this explicitly, like if we wanted to say, like, if we write it in here, right? We can write like character cast 97, right? And that will actually give us a character using 97. It'll turn 97 into the character. And so that'll give us A, right? Hopefully that makes sense to everyone. But yeah, using like casts, we can pretty much convert like any data type to any other data type as long as it sort of logically makes sense. And maybe not even to us. Like logically 97 obviously doesn't convert to lowercase a to us, right? But as long as it makes sense to the computer, then the computer will do it for us because the computer loves us. All right. You can also do some like really funky stuff with this. Like I know if you go into like the 200s or something, it'll give you some really like funky letters. And these are like still ASCII codes. They're just like not Latin characters. They're like further on. I think like if you go maybe even further, they're like more symbols. Yeah, things like that. But I guess it's actually just not showing up because these are like past the like base list. There's like an extended list. So you need to like change your encoding and everything. But yeah, you could pretty much like put whatever you want here and it'll correspond to like a certain character. Like even this is a character. It's just not any character that you can recognize, right? But cool. That was pretty much data types. And now that you know data types, you can pretty much like program in like any language you want to. I know that's a very broad sweeping statement, but it's kind of true. Like these kind of things you can just apply to anything. Like you can jump into Python, you can jump into like JavaScript. Obviously we did. They don't even have these types. You can jump into like C++, C, you can do like Ruby, anything you want. Like these kind of things, like these concepts are very applicable to like all of them. And like if there's anything that a language does differently than another one, it's like an easy search away and you can find out the behavior very easily then. And the more you use a language, the more you sort of understand and the more you sort of remember like what they do. Like obviously like me coming back to C++ in like, when was the last time I used this? In a while. Like I didn't remember the exact behavior of strings, but like if I search it up online, like I can pretty much just reference it really quickly and then you just know how to use it, right? And that's the same for like learning new languages as well. Like as soon as you understand these sort of concepts and like how they work most of the time, you can sort of extrapolate that and think, oh, this is what you expect to happen. And sometimes it's not true, but you generally have a good idea of like what things should be and what should do what, you know, things like that. But that was data types. Any questions? That's pretty much the lesson for today. Hopefully everyone's having a good middle of the week. It is Wednesday, and I'll see you all on Saturday for our office hours. I'm not completely sure what we're gonna do in these office hours. Maybe we'll do more Baba Is You gameplay, because that was actually pretty fun, and I bought the game, so we might as well get some game time out of that. Get the most out of our money, our limited budget for Spirit University. But that's gonna be fun. The Minecraft server is up for the community. I know a lot of people have been doing really cool stuff in there, and I've seen some really cool screenshots of like all the different rendering engines that people are using. So it's really cool. If you want access to it, make sure to join the Discord server in the description below. Make sure to follow us on YouTube and on Twitter. And what is it? Like and subscribe. Yay, we're YouTubing. Baba is hot, exactly. We're gonna see more of Baba probably on Saturday then. But we'll play it by ear. We'll see what we're gonna do. It's gonna be exciting. Yes, no problem. Thank you for joining us in this lesson. You're listening to all my battery-fueled rambling. And I'll catch you all on Saturday. Have a good night, everyone. Bye-bye.